In this video, I'm going to complete the notes on permutations, combinations, and the counting principle. And we're going to be answering the question, how can large groups of things best be organized and counted? So we're going to start looking into the counting principle by talking about this example. How many different ways can you order questions on a 5-question quiz? So we're going to look at this in depth. There are 1, 2, 3, 4, 5 questions on the quiz. And for the first question, I can choose between 1, 2, 3, 4, and 5. So that means there are 5 ways that I can do question 1. And now let's say I used question 3 that time. So now I can use questions 1, 2, 4, and 5. And now there are 4 questions remaining. So there are 4 options for the second question. And let's say I used question 5 for the second question. And now there are 1, 2, 3 questions left that I can use on my quiz. And maybe this time we use question 1, leaving only 2 possibilities left. And then if we use question 4, there's only 1 possible question to use. So to find out how many different ways that I could order the 5 questions on the quiz, I'm going to multiply all of the possibilities. The 5 possibilities for the first one, and then the 4 left over for the second question, the 3 possibilities left over for the third question, and so on and so forth. And this notation is called factorial. Or this expression rather, is notated this way with this exclamation point. 5 factorial is 5 times 4 times 3 times 2 times 1, and we can get that from the calculator for 120 ways to organize 5 questions on a quiz. So our answer here is 5 factorial, or 120 ways. The second example is very similar, except this time there are 8 questions on the quiz. So how many ways can I order 8 questions on a quiz? Well, if 5 questions was 5 factorial, this one's going to follow the same pattern. 8 factorial. Factorial values can get very large very fast. That's why we use the exclamation point. The counting principle can be extended to count multiple groups of things. How many different outfits can you make with 3 different shirts, 5 pairs of pants, and 4 hats? So let's see if we can diagram this out. For my shirts, there are 3 options. For my pants, I have 5 options. And for my hats, I have 4 options. So this is similar to the questions on the quiz, except I have, for shirts, 3 options. And these are my shirts. Let's see here. And then for pants, I have 5 choices. And then for hats, 4 choices. So we apply a very similar strategy here. We're still counting up options with multiplication, but this time we're not using the fancy factorial notation. We're just taking the different groups of things and multiplying them together. So 3 times 5 is 15. And 15 times 4 is 60. So there are 60 different outfits that can be created. In the next example, it's very similar. This time there are 6 shirts, 4 pairs of pants, and 2 hats. So 6 shirts, times 4 pairs of pants times 2 hats. 4 times 2 is 8. 6 times 8 is 48. So there are 48 outfits. Sometimes we want to know how many ways you can pick a limited number of items from a larger group. So suppose I want to create 4 class period schedule from a pool of 12 possible classes. Again, this is very similar to the first two examples. I have 1, 2, 3, 4 class periods, but then I have a total of 12 possible classes that I can pick from. 8, 9, 10, 11, 12. So there are 12 possibilities for my first period. And let's say we choose class number 8. And that would leave, so here there are 12 possibilities. I choose one, and now there's 1, 2, 3, 4, 5, 6, 7. We've chosen 8, 9, 10, 11, and 12. And now there are only 11 possibilities for a second period. And let's say we choose 1, leaving 2, 3, 4, 5, 6, 7, 9, 10, 11, and 12. So these are potential classes that we can pick for third period, and there are 10 that we can pick from. And maybe we picked 7, and now there are only 9 possibilities left that we can pick from for fourth period. So this is very similar to the factorial notation. In fact, it is a special type of factorial called a permutation, where we're going to just divide out. There were 12 possible, 12 factorial divided by 8 factorial, and what we're going to do to properly resolve this is use the permutation feature of the calculator. So that's 12 probability permutation 4. And the answer is 11880. And let's see, be sure you can see that in the light. And then I want you to see how that is the same as 12 times 11 times 10 times 9. So there are 12 possibilities for first period, 11 possibilities for second period, 10 possibilities for third period, 9 for fourth period, and then we're going to divide out the other 8 possibilities because we aren't ordering all 12 classes, we're only ordering 4 of the 12 classes. So to properly resolve questions like these, it would be 12 times 11 times 10 times 9, or in our calculator we would say 12 permutations of 4, and then that is equal to 1188 and 0. So 11,888. So there's that many ways that you can create a 4 class period schedule from a pool of 12 possible classes. And then here's a very similar example. How many different 5-number passwords can you create from the numbers 0 through 9 if repetition is not allowed? So there are 1, 2, 3, 4, 5 digits in my password. 0 through 9, so that's 10 possibilities for the first one, and then we can't repeat, so we only have 9 possibilities for the second digit, 8 possibilities for the third digit, 7 possibilities for the fourth, 6 possibilities for the fifth, because we're not allowed to repeat. So for each digit, the pool of numbers we can choose from gets smaller, and we would write that this way if we were going to use our calculator: 10 permutations of 5. And that is the same as 10 factorial over 5 factorial, because we stopped right there. We didn't do 5, 4, 3, 2, 1, so we need to divide those out. And our calculator has a nice function, 10 permutations of 5. That gives us 30,240, and then you can see that is the same as 10 times 9 times 8 times 7 times 6 times, not times 5, because we're only choosing 5 digits out of 10 numbers, and that is the same value. So at this point, you should pause the video and attempt to answer these two questions. What is the fundamental counting principle? And that's summarized here. It is basically counting up groups of things using multiplication, or counting up possibilities using multiplication. And then a permutation is explained here and in these two examples. So make an effort to pause the video and answer those two questions. This paragraph here gives a little more detail about permutations and how they're different from another thing called combinations. And what we want to learn about in combinations, we want to limit ourselves further so that when we're drawing from a group of things, the order in that group does not matter, or it's not considered distinct. So in the previous example, for the permutations, 1, 2, 3, 4, 5 and 5, 4, 3, 2, 1 would be considered different. But now for combinations, we are going to consider things like these the same. So ordering things differently won't create new possibilities. So how many different ways can 4 students be chosen from a class of 30? Well, we have 1, 2, 3, 4 students, and there are 1, 2, 3, all the way up to 30 possibilities for the first one. And then 1, 2, 3, all the way up to now there are 29 remaining possibilities for the second one. And then 28 possibilities remaining for the third, and 27 possibilities remaining for the fourth student. But in order to remove repetitions, not only are we going to take 30 factorial and divide out the 26 factorial, that is, we didn't continue all the way down to 1, going times 26, 25, 24, 23, we're dividing all that out. We're also going to divide out the 4 different ways we could order the 4 that we did choose. And we have a handy feature on our calculator that does this for us, and that is a combinations function. So 30 combinations of 4 different ways I can grab things from 30 without concerning myself with order. 27,405. So 27,405, and in our calculator that would read 30, choose 4. And now we have a similar example. We're going to choose 3 out of 20 students will be selected to represent Cedar Ridge. So we're going to take 20 students and choose 3 of them. And this is a good place to help illustrate the difference between combinations and permutations. So suppose our 3 students are Bob, Sue, and Joe. There are 3 factorial ways, or 6 ways, that I can put Bob, Sue, and Joe in order. We can do Bob, Sue, Joe, Bob, Joe, Sue, Sue, Bob, Joe, Sue, Joe, Bob. And last we can do Joe, Bob, Sue, and Joe, Sue, Bob. So in a combination, those 6 things are all counted as 1. In a permutation, those 6 things would be counted as 6 different things. So with combinations, order does not matter. It does not create distinct possibilities. With permutations, it does. And here's some more explanation of combinations and the formula that your calculator is using when it computes this. And we will go ahead and run that out. The answer is 1140. And I think it's important to note that permutations of the same size, if I were to permutate 20 permutations of 3, will always be larger than 20 combinations of 3, because there's roughly 6 times as many, because in combinations, these 6 entities only count as 1, but in permutations they count as 6. Okay. So determining whether we're dealing with a permutation or a combination is half of the game here. Then after you've done that, you can just let your calculator do the hard work most of the time. So take a minute, pause the video, write down your understanding of what a combination is, and then see if you can answer these 4 questions. Okay, so is this number 1 about Hong a permutation or a combination? Huang has homework in 6 subjects. She is deciding what order to complete them. So if we went science, history, math, English, that's going to be different than English, history, math, science. Order does matter, so this is a permutation. And it would be 6 factorial ways, or 6 permutations of 6. A group of 24 people need to take an elevator to the top floor. They will go in groups of 8. They are deciding who will take the elevator on its second trip. So they're going in groups of 8. We're on the second trip. That means we only have 16 people left. So 16 choose 8. This is a combination, and it is a combination because we don't care what order the people get on the elevator. We just care that we chose 8 of those people. A team of 17 lacrosse players needs to choose 2 players to refill the water. Again, this is a combination because we don't care what order those players go to get the water. We just care that we picked 2 out of the group of 17. And now, for number 4, a group of 40 people are going to run a race. The top 3 runners earn gold, silver, and bronze medals. So that would be a permutation because the order that the first 3 people place matters. If Joe, Mike, and Sally come in first, second, and third, that is different than if Mike comes in first, Sally comes in second, and Joe comes in third. So 40 people, permutations, 40 permutations of 3. 3 permutations of 40. We have a group of 40 people, and we want to select any 3 of them, but we want to keep the order distinct. So first, second, third will be different depending on which 3 people come in. Okay, so discerning whether you're using permutations or combinations is a big part of the challenge here. And again, it all has to do with whether or not order matters. Here are some special cases. Sometimes a sample space or the number of possibilities is small enough to just list out. A spinner can land on red, blue, yellow, or green. In fact, pause the video and make an effort to do number 1 right now, and then I'll reveal the answer. So red, blue, yellow, or green, there are 4 possibilities for the spinner. You flip a coin, and there are 2 possibilities for the coin. So we should have 4 times 2 for 8 possibilities total, but it's really easy to write everything out. Red, blue, yellow, green, and then heads, 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 heads. And we also have red, blue, yellow, green, and tails, 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 tails. So those are all 8 possibilities right here. 4 possibilities from the spinner, 2 possibilities from the coin. How many different ways can you arrange the letters in the word washtub? Well, this is a direct counting principle problem. There are 1, 2, 3, 4, 5, 6, 7 letters in washtub, and there are 7 possibilities for the first one. And then we've used 1 letter, now there's only 6 possibilities. We use another letter, now there's 5 possibilities. We use another letter, now there's 4 possibilities, and so on and so forth. So the answer to number 2 is 7 factorial. Number 3 is a little bit different because we'll be dividing out repeated letters. There's 11 letters in Mississippi, so it follows a pattern similar to this one, but then we have to go and divide out all the ways we could order all the repeated letters. So there are 4 S's in there, and we could order those 4 S's any way we want, so we have to divide out 4 factorial S's. And there are 4 I's, so we have to divide out 4 factorial I's. And then there are 2 P's, so we have to divide out the 2 different ways that we could order the P's. So the fact that there are repeated letters limits the number of possible ways we could order the letters in this word. And you can work this out with your calculator, especially if you are good with your fraction template. 11 factorial over 4 factorial times 4 factorial times 2 factorial. Oops. And there are all your possible ways. So getting good with the calculator and the probability menu is going to be important for this unit. How did we deal with the repeated letters in Mississippi? We divided them out. So take a moment to write down an answer to that question. Allowing for repetition can change our approach slightly. A simple password is 5 characters long. Chosen from a group of 8 possible characters, repeats are allowed. So, again, if we wanted to diagram this out a little bit, 3, 4, 5, 6, 7, let's see. The password is 5 characters long. So, there's our first part of our password, the second digit, the third, the fourth, and the 5th digit. Repeats are allowed, and we can choose from 8 characters. So there's 8 options for 1, but then it's okay to repeat digits. So if I was choosing between 0, 1, 2, 3, 4, 5, 6, and 7, so 8 options there. Repeats are allowed, so I'm not going to cross anything out, and I still get to choose from 8 possibilities. So that would be times 8, and then we can repeat again. So we're going to end up using exponents, because for each of the 5 digits in the password, we can use all 8 characters. So when you allow for repetition, things do change. So there were 8 different possibilities for each of the 5 spaces. So we say 8 to the 5th power, and see if you can answer this question right here. And then finally, a 6-person student council will be chosen from a group of 10 seniors and 8 juniors. So here we're going to be doubling up on our technique, or sometimes we'll have to apply 2 techniques at once. The council must be composed of 4 seniors and 2 juniors. So the 4 seniors and the 2 juniors makes up our 6-person council, but we're choosing the seniors from a group of 10 and the juniors from a group of 8. And we don't care what order they're chosen, just that we have 4 seniors, and we don't care about the orders of the juniors, just that we have 2 of them. So that's 10 seniors selecting 4 from the group of 10 without concern for order, times 8 juniors, but we're selecting 2 from that group of 8. And again, if you get good with your calculator here, you can work that out pretty swiftly. 10 seniors, choose 4, times 8 juniors, choose 2. Close parentheses, and there are 5,880 ways that we could create a student council from those options. Okay, and what do all counting principle problems have in common? You should be picking up on the fact that we are always using multiplication. So take a minute to summarize your notes, and then if you log into Kia, you get the opportunity to practice what you just learned.